The most capable hydraulic robot ever built could rip a car door off its hinges. Boston Dynamics scrapped the whole system anyway. Atlas HD could produce over 400 pounds of force from a single joint. Boston Dynamics threw out every hydraulic line, every servo valve, every accumulator, and replaced it with electric motors that produce a fraction of that peak force. That is not a downgrade they stumbled into. That is a deliberate bet on a different definition of what a useful robot actually needs to be. Before Atlas went electric, two failure modes defined every attempt to put a robot next to a human. The first was rigidity. Industrial arms like the Fanuc M2000 are bolted to the floor and caged behind barriers because any unexpected contact transfers directly into the object, or the person, in their path. The second was hydraulic unpredictability. Early Atlas, the DARPA-era version, weighed about 350 pounds and operated at 3,000 psi. If you pushed its arm, it pushed back with the full pressure of a hydraulic system that does not yield. Working alongside that machine is not a collaboration. It is a proximity hazard. Backdrivability is the property that lets you move an actuator from the output side, meaning you can push the joint and the motor gives way, rather than fighting you. In a hydraulic system, pressure in the line actively resists external force. Compliance requires deliberate valve actuation. There is always a lag, and that lag is measured in milliseconds that matter when a human arm is in the path. Electric motors, specifically brushless DC motors paired with low-ratio gear trains or series elastic actuators, behave differently. When external force is applied to the joint, the motor backdrives. The rotor spins in reverse, generating a small back EMF that the controller reads as a torque disturbance. That signal arrives in under a millisecond. The controller can then modulate output torque in real time to yield, to match, or to resist, a behavior called impedance control. The core equation is simple. Torque output equals inertia, times angular acceleration plus damping times angular velocity. By tuning those two coefficients in software, engineers can make the same physical joint feel like a rigid arm, a compliant spring, or anything in between. That tunability is the entire reason the trade was worth making. The backdrivability gain came with three concrete costs that Boston Dynamics had to accept in writing, effectively, in every design review. First, peak force density. Hydraulic actuators deliver roughly 5 to 10 times the continuous force per unit volume of an equivalently sized electric motor. Electric Atlas compensates with mechanical advantage and optimized joint geometry, but it cannot replicate the raw output of hydraulic Atlas at the same weight. That is a permanent ceiling on payload capacity for this generation. Second, thermal management. Brushless motors running high-torque maneuvers saturate thermally in ways hydraulics do not, because hydraulic fluid carries heat out of the actuator as it circulates. Electric systems accumulate heat in the windings and the drive electronics, which sets hard duty cycle limits. The robot must pace itself or throttle output. Third, gear train compliance. High-ratio gearboxes like the harmonic drives widely used in humanoid joints introduce reflected inertia and gear stiction that partially offset the backdrivability benefit. Boston Dynamics published torque control research indicating they use low-ratio or direct drive configurations specifically to minimize this effect, accepting lower torque multiplication in exchange for cleaner force feedback. The citation here is their 2022 ICRA paper on electric Atlas whole body control. Each of those three trade-offs was a negotiation. What does this robot need to do, and what can we leave on the table? The decision Boston Dynamics made in 2021 is now the central design fork every humanoid robot company is navigating simultaneously. Figure AI chose electric with custom actuators and is targeting automotive assembly lines, an environment where collaborative compliance matters. Apptronik's Apollo developed partly with NASA heritage from the Valkyrie program, uses series elastic actuators explicitly to get safe force control in human-occupied spaces. Tesla's Optimus has iterated publicly toward low-ratio electric drives with integrated torque sensors in the wrist and ankle joints. None of these companies chose hydraulics. That is not a coincidence. It is a revealed preference across the entire industry for the same trade Boston Dynamics made. The downstream effect is visible in the adjacent market. Companies building the gear trains, the torque-dense motor laminations, and the force-torque sensors for compliant joints are now critical suppliers to an industry that did not exist at scale 5 years ago. Harmonic Drive AG, whose flex-spline gear technology appears in the majority of commercial humanoid joints, has seen its components become a choke point. The compliance architecture Boston Dynamics chose did not just define Atlas. It drafted a parts list that the entire humanoid sector is now ordering from. Here is the constraint nobody in the industry is advertising. Backdrivable electric actuators are safe because they yield, but yield and load-bearing are in direct tension. The moment a humanoid robot needs to carry more than roughly 30 to 40 kilograms or operate in an environment where external forces are large and unpredictable, think construction, not assembly, the compliance architecture starts costing more than it gives. The thermal ceiling on electric drives means sustained high-load tasks are not on the table with current motor technology. When that ceiling is hit, the field will face a second fork, accept the payload limit permanently, or develop a hybrid actuation system that recovers some hydraulic force density without sacrificing the impedance control that makes these machines safe. That hybrid does not exist in a production humanoid yet. The company that ships it first will define the next generation of what working next to a robot actually means. The backdrivability problem is solved at the joint level, but getting that joint to do something useful, to walk, to balance, to catch a falling object, requires a control architecture that operates 10 times faster than human reaction time and uses a completely different mathematical framework than anything in classical robotics. That framework is the mechanism this entire field runs on, and it is what the next episode traces from first principles. If you followed the logic this far, the next one pays off the part we did not have time to get to today. The joint compliance problem is one layer of the stack. The control loop that runs on top of it is where the real engineering lives, and that is exactly where the next traceroute episode starts. Follow the channel so you do not have to remember to come back.